In this video, we're going to be talking about section 4.2, which is called reduction of order. So I'm just going to remind you about what we did in section 4.1. So in 4.1, we looked at nth order homogeneous differential equations. So basically, we have an of x is not equal to 0. This is a linear differential equation, and it's the nth order because you have the nth derivative. So what we said in section 4.1 is that if you have n different solutions to this differential equation here, and they're linearly independent, they form what's called a fundamental set of solutions. So what we talked about in class was that if you have a fundamental set of solutions, then you can find the general solution as just a linear combination of these. So basically what that means is if y1, y2, all the way up to yn are n linearly independent solutions, then your general solution is just some constant times your y1 plus a constant times your y2, where these c's are arbitrary constants. So now what we're going to do is we're going to look at a general solution for a second order differential equation. So here, if we just have a second order differential equation, again, we need two linearly independent solutions to find a fundamental solution set. And then if we have those two linearly independent solutions, then our general solution is just a linear combination of these two. Okay, so what does it mean for these to be linearly independent functions? So this is, again, is a reminder of what we did in section 4.1. So if you have linearly independent functions, then what we say is that if you form this combination and you set it equal to 0, if these two functions, y1 and y2, are linearly independent, then the only values that can be true is that c1 and c2 must be equal to 0 if these are linearly independent. So what we're going to do is we're going to use this fact to say, okay, what if we know a solution y1, how do we find a solution y2 to our differential equation? So in other words, we assume that we know one of these solutions to our differential equation, our second order differential equation, and we're looking for y2. So just looking at this a little bit closer, what it means for these two to be independent is basically that they're not constant multiples of each other. So you can't say y1 is some constant multiple of y2. So here you move this to the other side, you divide by the c1, and you basically get this constant here. So what you're saying is that there is no constant so that you can say y1 is a constant multiple of y2. So we're going to go a little bit farther, and what this basically means is that y1 over y2 can't be equal to a constant. So if it's not equal to a constant, then it has to be equal to a function. So we're going to use this fact, and we're going to actually figure out what a proper function should be for you to figure out then what y2 should be. So what we're going to assume is we know y1. We know one of the solutions to our second order differential equation. To find y2, we're going to reduce the order. What that means is we're going to actually substitute in y2 is an unknown function u times our known function y1. So here we're assuming we know y1, we don't know what u is, but we can say y2 is equal to some function u times y1. And so now what we do is we substitute this into the differential equation. When we do that, we're going to find a differential equation in terms of u that we can actually solve. Okay, so for example, let's assume that y1 is e to the x, and that is a solution to this differential equation. So again, if I take the second derivative of e to the x, I'm going to get e to the x. E to the x minus e to the x is 0, so it is the solution. So now I want to find a general solution. What that means is, since this is a second order, I need two different linearly independent solutions. So I need a y2. So what we're going to do is we're going to assume that y2 is equal to u times y1 or u times e of x. We substituted this into the differential equation. So here we're going to take the second derivative of our u times e to the x minus our y. So again, our y is u e to the x, and we want to set this equal to 0. So we're going to try to find a differential equation for u. That's our goal, is to find a differential equation for u. So if we take the second derivative of u times e to the x, again we have to use the product rule. So remember the product rule. So we're going to have the first times the derivative of the second plus the second times the derivative of the first. So here this is what's going to go in place of this first term. So when we So that is our first derivative, and then our second derivative, we had to take the derivative again of this. So again, the first times the derivative of the second, plus the second times the derivative of the first gives us this part. First times the derivative of the second gives us this. Second times the derivative of the first gives us this part. So that's what's going to go into our differential equation. So this whole first part here is our y double prime. This is our minus our y. So if we look at this, this u e to the x cancels with this u e to the x. We have two u primes here, and we have a u double prime. And we have all of this has an e to the x term in it. So what you can do is you can factor it out. Here this is the same thing as this one, so we have two of those. So we're going to have u double prime plus 2u prime e to the x is equal to 0. But what this means is we actually have this differential equation because e to the x is not actually ever equal to 0. So we have this differential equation for u. So now this is a differential equation that we want to try to solve. If we find u, then we get our second solution. We get our second solution y2 because y2 is just u times y1. Okay, so looking at this, what we're going to do is we're going to do a simple substitution. We're going to let w equal u prime. So that means this is going to be a w and this is going to be a w prime. So we get this equation. Everybody already knows how to solve this. This is a separable equation. We separate variables, so we have dy dx is equal to negative 2w. Separate the variables. Then we integrate both sides, and we get what what w is. But remember, w is just our u prime, so we're really looking for u. So now what we do is we solve this for u. du is equal to a e to the negative 2x dx. Integrate both sides. That's going to give us u is equal to, when I integrate this, I'm going to have this term plus another constant. So now we go back and we look at y2 is u y1. So that means this is our form for y2. Just multiplying the e to the x through, we can simplify this just a little bit farther. So here, a and b are arbitrary constants. We just want one other solution, so we can let b equal 0. We can let a equal negative 2 just to make it look nice. And so if b is equal to 0, this term goes away. If a is negative 2, then this is e to the negative x. Now remember, we want this to be 0 because this has the e to the x term in it, so we want to make sure a is not equal to 0 here. If a is equal to 0, then we just have a combination of our y1, which is not what we want. So here, e to the negative x is the second solution. E to the negative x and e to the x are linearly, this should be independent in both solutions to the ODE. So once we have our y1 and our y2, then we can say any linear combination of these is our general solution. We can also actually generalize this to a formula. So your book goes through how to actually do this. We're not going to do this in this video. So here, what you do basically is to use this formula, you have to change your second order differential equation so that your coefficient of y double prime is 1. So then what you have here is going to be your b of x divided by a of x. That's going to be p of x. And then this is your c divided by a. So now what we have is, to find our y2, we can say this is y1, the integral of e to the integral of p of x dx divided by y1 squared. Integrate that whole thing. So let's assume that we know that y1 equals x to the fourth is the solution to this differential equation. We want to find a second solution, y2, using the formula. Okay, so here we rewrite this. We divide everything so that this coefficient is 1. So we divide everything by x squared. When we divide by x squared, we're going to have a negative 7 over x here and a 16 over x squared here. So our p of x is negative 7 over x and our q of x is 16 over x squared. We use our formula for y2. So here we plug in, this is our p of x. This is the thing we're going to integrate first. This negative and negative is going to give a positive. We're going to have 7 natural log of x there. So we have e to the 7 natural log of x. We can bring that 7 up as the exponent. When we bring the 7 up at the exponent, then we have the e in the natural log, so we're going to be left with just x to the 7th there. This bottom simplifies to x to the 8th. So really what we get is we have the integral 1 over x in here, which we all know is natural log of absolute value of x. This is our y2. So we had y1 is x to the 4th, y2 is x to the 4th natural log of x. So now what we have is this is our second solution. We can find our general solution. But just to show you that we actually get the exact same thing, whether or not we do it by the formula or whether we do it by the substitution method, let's do the substitution method. So here we say y2 is u y1, just like we did last time when we're plugging this into our differential equation. So we're plugging in this everywhere we saw y. So we have y double prime, we have y prime, and here's our y term. So we need all these derivatives. The first derivative here, first times the derivative of the second, plus the second times the derivative of the first gives us this. Take the second derivative. Again, here we had to use product rule twice, so we had the first times the derivative of the second, plus the second times the derivative of the first, so we get these two terms. First times the derivative of the second, plus second times the derivative of the first, we get these two terms. We can simplify. The 4 plus the 4 gives us this 8. So here we have what our second derivative is equal to. Again, we're taking this, plugging it in here, taking this term and plugging it in here. So we can simplify everything now. So everything is plugged in. We simplify. So notice here you have a u prime and a u prime. Here you have a u, and u. The thing to notice though is that this is a 12, this is 16, so we get positive 28x to the 4th u minus 28x to the 4th u. So these terms actually cancel, all the u terms cancel. So we're just left with a u prime term. So here we have an x to the 5th u prime and an x to the 6th u double prime. So this is what we end up with as our differential equation. Again, x to the 5th is not equal to 0 everywhere, so we're going to assume that this is our differential equation. We do our substitution, so we let w be u prime, so now we have a separable equation. We can separate, we solve this, and we get natural log of w is minus natural log of x, or w is just 1 over x. So that means our u prime is 1 over x. We integrate to get u, we get natural log of x, and then we get the exact same thing as we did before, because remember y2 was u. There's our u times our y1, and our y1 was x to the 4th. So we get the exact same answer. Okay, so all of these problems, all they do is they use this exact same substitution method. You can either substitute or you can actually use the formula to get a second fundamental solution for your differential equation, given you have one already. And that's all of section 4.2.